Hello everyone. In today's lecture of Chemical Engineering Thermodynamics, we are discussing the equation of state for real gases. If our ideal gases and real gases. So differentiate between real gases and ideal gases we are already discussing. So perfectly real gases, what should be the equation of state can be written. Okay. So that fundament we will clear in this lecture. So perfect gas law is inadequate to explain behavior of real gases. એટલે આઇડિયલ ગેસ માટે જે પરફેક્ટ ગેસ લો છે એ શું કરે છે રિયલ ગેસ માટેનું એનું બિહેવિયર નક્કી કરે છે અથવા તો બિહેવિયર એનું ડિસાઇડ કરે છે. ફોર રિયલ ગેસીસ ટુ બિહેવ આઇડિયલી, so for real gases it behaving like ideally, so the molecule of interaction should be negligible. કારણ કે ફ્લુઇડ છે એ કઈ આઇડિયલ કન્ડિશનની અંદર વહેતું હોય, બરાબર, ફ્લો થતું હોય, so there is no molecular interaction with each other, so that's why we consider it's negligible. At a low molecular volumes or a high pressure, molecules comes very close to each other and molecular interaction cannot be neglected. Where first it having a fluid having a low molar volumes or high pressure, molecules comes very close to each other. High pressure હોવાને કારણે molecules છે એ બધાના એકબીજાના નજીક આવી જશે, બરાબર. તો આવી કન્ડિશન પર મોલેક્યુલનું ઇન્ટરેક્શન કેન નોટ બી નેગ્લેક્ટેડ. સો the perfect gas law may be viewed as an approximation of describe the behavior of ideal real gases at an ordinary pressure as the limiting behavior of real gas at low pressure. So many equations of state have been proposed to explain the actual behavior of gases. So first one is see the limiting condition. Equation of state in general, it should be satisfy certain limiting condition, and these they are follow. First, all equation reduced to the ideal gas equation at low pressure, that is PV is equal to RT. એટલે કોઈ પણ આઇડિયલ ગેસ હોય તો એ રિડ્યુસ થઈને સામા કઈ કન્ડિશનમાં ફોલો થવું જોઈએ, બધા જ ઇક્વેશન PV is equal to RT આઇડિયલ ગેસ ફ્લો, બરાબર. અને જે આ P is tend to 0 એ કન્ડિશનને ફોલો કરતું હોવું જોઈએ કયા પ્રેશર પર, લો પ્રેશર પર, બરાબર. So equation reduced to the ideal gas equation where P is at low pressure PV is equal to RT and P tends to 0. The slope of PV isothermal against P may be equal to, greater than or less than 0 at present tends to 0. Okay, at pressure tends to 0 मतलब PV isotherm છે, બરાબર. P અને વોલ્યુમ અને પ્રેશર, બરાબર. તો એની અંદર P કેવો છે એ કોના જેટલો હોય છે, એ ઇક્વલ ટુ બરાબર હોય, વધારે હોય અથવા તો ઓછો પણ હોય, બરાબર. પણ પ્રેશર ટેન્ડ્સ ટુ 0, પણ પ્રેશર કેવું હોવું જોઈએ, ઘટતું હોવું જોઈએ. This true for the slope of compressibility factor versus P curve. So that is either કઈ રીતે હોઈ શકે, ડેલ PV, બરાબર. પ્રેશર અને વોલ્યુમ ટર્મ્સની અંદર ડેલ વિથ રિસ્પેક્ટ ટુ P is tends to 0. It constant temperature T, it should be less than or equal to 0 but P tends to 0. અથવા તો we can write as a del upon del PV upon del P at a T which is પહેલા તો પહેલા કન્ડિશનની અંદર એ ઓછો છે અને બીજા કન્ડિશનની અંદર એ વધારે છે અને બંનેની અંદર ઇક્વલ ટુ કન્ડિશન તો આવી જ જાય છે. ઓકે, So in second condition, del into PV in divided by rho P at T constant temperature, it is greater than or equal to 0 where P tends to 0. This condition should be satisfied. Next, third one is that the PV curve at a constant temperature પર pressure અને volume નો curve should be exhibit a point to inflection at a critical point. બરાબર કે P અને V જે curve છે PV curve constant temperature એટલે કે પ્રેશર અને વોલ્યુમનો જે કર્વ છે કોન્સ્ટન્ટ ટેમ્પરેચરે, તો એની અંદર જે ક્રિટિકલ પોઈન્ટ છે એ કેવું હોય છે, ઇટ શુડ બી એક્ઝિબિટ ક્યાં થવો જોઈએ, ક્રિટિકલ પોઈન્ટ તરફ થવો જોઈએ. સો ડેલ પી બાય ડેલ વી એટ TC constant temperature equal to 0 where integration of this, okay, differentiation, so del square P upon del V square at constant temperature TC, that is critical temperature equal to 0. Okay, next fourth one is that the PT curve are linearly except at very high density. That means in pressure temperature curve the value of P and T curves are linearly accepted at very high density. So it should be del square P by del T square at constant volume equal to 0. Okay, so exactly what happened, the relation is not exact, T tends to infinity and it is approximate other condition. So at a high densities it should be less than 0, del square P by del T square constant volume, it should be less than 0. This inequality means that PT curves are convex upward to the T axis. A few of the commonly used equation of the state are discussed in following section. So next is that van der Waals equation. Van der Waals equation, this equation is also important for the examination. So van der Waals equation proposed to following equation to explain the PVT behavior of real gases. van der Waals से इक्वेशन एक्सप्लेन કર્યું PVT behavior ને easily explain કરી શકાય real gases માટે, એટલા માટે. So van der Waals equation is that P plus A by V square into V minus B equal to RT. This equation is known as a van der Waals equation. Okay, P plus A by V square into V minus B equal to RT, where A and B are called for the van der Waals constant and A and B શું છે, van der Waals constant છે. This equation is cubic in volume and below the critical temperature. આ જે equation છે generally શાના માટે છે, below critical temperature માટે. You should have to remember that this equation is for only below the critical temperature and is in the form of cubic volume, it having the meter cube, that means cubic volume. Okay, next there are three real roots. The largest is the vapor volume and the smallest is the liquid volume, and intermediate root has a physical significance. Okay, તો આ ઇક્વેશન ની અંદર જનરલી કેવા છે, ત્રણ રૂટ છે. ફર્સ્ટ પહેલું છે વેપર વોલ્યુમ, બરાબર, વેપર વોલ્યુમ ઇઝ ઇન ધ સ્ક્વેર ટર્મ્સ, બરાબર, જે V સ્ક્વેર ના ટર્મમાં છે. એન્ડ સ્મોલેસ્ટ જે છે, સ્મોલેસ્ટ ધ લિક્વિડ વોલ્યુમ, સ્મોલેસ્ટ શું છે, લિક્વિડ વોલ્યુમ છે. અને ઇન્ટરમીડિયેટ રૂટની અંદર શું છે, there is a no root has a no physical significance, where P is the saturation pressure. P શું છે, saturation pressure છે. And the smallest and the largest root corresponds to molar volumes of saturation liquid and saturation vapor respectively. The perfect gas equation failed to explain PVT behavior of real gases at the volume occupied by the molecules of real gas and forces of interaction between them to negligible is an ideal gas. Van der Waals equation takes to account these two features real gas by incorporating certain corresponding factor in the terms of pressure and volume. So to find the gas equation, the perfect gas equation છે that is not actually we can find the PVT behavior, pressure, volume and temperature behavior of real gases. So the van der Waals occupied the new equation in which molecules of real gases and forces acting between them are negligible as in the ideal gas. Ideal gas ની અંદર જેમ negligible કરી શકીએ છે એમ આની અંદર પણ ideal gas ની અંદર પણ આ રીતે પણ આપણે શું કરી શકીએ છે negligible. Van der Waals equation takes into account these features real gas by incorporating certain correction factor in a pressure and volume terms of the gas equation in order to find a correction terms to compensate for the attractive force between molecules. Okay, and consider the force to attraction by molecular hitting the wall of container. The attractive force is directly related to the number of molecules per unit volume and frequently for the molecular collision. So the latter in the proportional to the number of molecules per unit volume. In short term, the net attractive force is proportional to 1 upon V square, where V is the molar volume of the gas and the actual pressure P of the gas is less than the ideal pressure calculated by kinetic theory by A by V square, where A is a constant or the pressure term in the terms of ideal gas equal to should be replaced by P plus A upon V square. Okay, so this phenomena we can see in this. Okay, P plus A upon V square into V minus B equal to RT. The center of two identical molecules are at a distance equal to the molecular diameter of instant of their collision with each other. The molecular separation of collision cannot be smaller than this distance, since each molecule is surrounded by a forbidden volume that cannot be penetrated by another molecule. The effective volume of the gas will be less than the actual volume. જે molecule effective volume છે બરાબર, so that should be penetrated by effective volume, and for the gas it will be less than the actual volume. The volume terms in the ideal gas equation replaced by V minus B, where B is indicated that forbidden volume per mole of gas, and equation 3.29 result is incorporating this corrective P and V terms in ideal gas equation. PV is equal to RT. P should be in the term of A by V square, and V is V minus B equal to RT. This consists of the constant in the van der Waals equation can be evaluated utilizing the limiting condition 3.28. This should be obeyed by any equation of state. Applying this criterion, equation 3.29, and we get Vc equal to 3b, that means 3b is equal to Vc, and Tc is equal to 8 upon 8a upon 27 upon Rb, or Pc is equal to Rtc upon 2b minus A upon net B square, where A and B are the van der Waals constant, and what is the value of A and B? A and B की value हम VC, TC एंड PC के अंदर अगर हम पुट करेंगे तो उसके ऊपर से हम कोई भी इक्वेशन की PVT बिहेवियर हम फाइंड कर सकते हैं। सो वांडरवाल इक्वेशन की A की वैल्यू कांस्टेंट A इज इक्वल टू 27 R square TC square and divide by 64 PC, and B की वैल्यू क्या होगी RTC डिवाइड बाय 8PC। Okay, so this two constant values are put into equation number 3.29 and we get the PVT behavior. Okay, ideal gas equation and van der Waals equation, both more clear when we put this value into the equation.